We usually write numbers in decimal system, or in other words base 10, where the digits represent different powers of 10. But we can use other ways to write numbers. For example, we can use base 6 or base 2, which is used in computers. Now, just as we can use natural numbers as bases, we can also use negative numbers like -5 or -12 as number bases. Numbers that can be written as a fraction are called rational numbers. We can also use these numbers to create unique number systems. Real numbers include all of the previous sets, but they also contain irrational numbers, like the square roots, and transcendental numbers, like pi or e. And yes, we also can create number systems based on the real numbers. Beyond real numbers, we have imaginary numbers. We also can create imaginary number bases, and they can even express real numbers. Finally, when we combine real numbers and imaginary numbers, we get complex numbers, and as you might guess, this can be the base for the number systems as well. But to understand those unusual number systems, let's first go back to the natural number bases. In any base b, digits represent different powers of b. And if b is an integer bigger than 1, in base b we use digits from 0 to b-1. So for example, in base 7 we would use digits from 0 to 6 and they would represent different powers of 7. We can also add the decimal point to include negative powers and be able to express fractions. But maybe in this base it should be called a septimal point. From now on, the index in the bottom right corner will represent the base of the number. Numbers without an index will be always in base 10. We can easily convert numbers between different bases. We just multiply the digits by the corresponding power of the base and add them all up. But there is one important thing we need to remember. When we want to convert a number to a base different than 10, we need to perform calculations in that base. In this example, we want to convert a number from base 9 to base 5. In base 5, we can use digits from 0 to 4. So we have to write 8 as 1 3 in base 5, and we also have to write 9s as 1 4. Now we just multiply each digit by the corresponding power and add them up. But not forgetting that we make all calculations in base 5, so 4 times 1 4 is equal to 1 to 1, and not 56 like in base 10. One last thing before we talk about negative number bases. The special case of base 1. According to the rule that the other natural number bases obey, that in base b we use digits from 0 to b-1, in base 1 we would only be able to use digits 0, so we wouldn't be able to express any value except 0. So to be able to express integers in this base, let's assume that we can use any sign as the only digit. This base isn't very efficient in expressing bigger values, because the value of a number is also equal to its length. When we talk about number bases, there's only one number that cannot be a number base, and that is 0. 0 raised to any integer is just equal to 0, and 0 raised to the power of 0 is undefined. So base 0 can't exist because it wouldn't be able to express any value except 0. Surprisingly, all other real numbers that you can think of can be a number base, and all those bases can express integers. So let's start exploring those unique number bases from the negative numbers. In base -10, digits represent different powers of -10. The odd powers are negative and the even powers are positive. But what digits should we use in this base? In positive number bases, we use digits from 0 to base -1. To be able to express all integers in negative number bases, we will use digits from 0 to the absolute value of the base -1. So in base -10, we will use the same digits as in base 10. But the numbers written in base -10 don't look like those in base 10. Because the odd powers of -10 are negative, the numbers in this base are built differently. For example, to express 473 in base -10, we first have to take 5 hundredths, then add 3 -10s, and add 3 units. In base -10, we also can express negative values without using the minus sign. For example, this number is equal to -95. All negative values have an even number of digits when they are written in negative base, and all positive values have an odd number of digits. Number bases of different negative integers behave like the base -10. After integers, we have rational numbers. Rational numbers are all fractions where the numerator and the denominator are integers. First, let's look at bases of form 1 over some integer n. For example, base 1/3. In this base, digits represent different powers of 1/3. That is 1, 1/3, 1/9, and so on. But if we write the decimal point, we get negative powers. which give us 3, 9, 27, and so on. All those values are just powers in base 3 but reversed. So to be able to express any number in base 1/3, we only need the same digits as in base 3, so 0, 1 and 2. And also numbers written in base 1/3 are just reversed numbers in base 3. For example, 32 and 2/3 in base 3 looks like this. So in base 1/3 it is written like that. And that is true because after multiplying the digits by the corresponding power of 1/3, we get 32 and 2/3. That is true for any base that is of form 1 over some integer n. Another fact is that in all bases of form 1 over some integer n, we use digits from 0 to the absolute value of n minus 1. Now let's look at the fractions of form a over b, where a and b are not equal to 1. First let's see the example where a is bigger than b. For instance, base 7/3. In this base, as in all other bases, digits represent different powers of 7/3. But what digits should we use? Because we have 7 in the denominator, let's first take a closer look at base 7. To convert numbers to base 7, we can just multiply each digit by the corresponding power and add them all up, not forgetting that we have to perform all calculations in base 7. But there is a faster way that allows us to convert numbers between bases. Let's say that we want to convert 265 to base 7. First, we divide 265 by 7. We get 37 and a remainder of 6. Then we divide 37 by 7. We get 5 and a remainder of 2. Now we divide 5 by 7. We get 0 and a remainder of 5. It means that 265 in base 7 is written as 526. Why does this method work? We divided 265 by 7 and we got 37 with a remainder of 6. That means we can write 265 as 37 times 7 plus 6. Next we divided 37 by 7, so 37 can be written as 5 times 7 plus 2. After multiplying everything out, we get that this is equal to 5 times 7, which is equal to 7 to the power of 2, plus 2 times 7 to the power of 1, and plus 6 times 1, so 7 to the power of 0. Now let's see how would this work in base 7/3. We start the same. We divide 265 by 7. Now we do something different. We multiply 37 by 3. Then we divide 111 by 7. We get 15 and a remainder of 6. So we multiply 15 by 3 and divide by 7. We do it until we get 0. It means that 265 in base 7/3 looks like this. And again, why does it work? We divided 265 by 7, so we can write it as 37 times 7 plus 6. Then we multiply 37 by 3, it means that we can write 37 as 111 divided by 3. We can write it like this. Then we can write 111 as 15 times 7 plus 6. Then we can write 15 as 45 divided by 3. And so on. After multiplying everything out, we get this. So we know that this is a representation of 265 in base 7/3. Because the digits are the remainders when we divide by 7, we know that in base 7/3 we can use digits from 0 to 6. This trick is really useful when we want to convert numbers to fractional bases. But it only works if the numerator is bigger than the denominator. But now let's look at number bases where the denominator is bigger. We have already seen that numbers written in base 1 over n are just reversed numbers written in base n. It also means that numbers written in base a over b are reversed numbers written in base b over a, because a over b to the power of n is equal to b over a to the power of minus n. Let's look at base 3/7, the reverse of 7/3. 265 was written as 64366 in base 7/3. So in base 3/7 it will be written as 6.6346. And we can see that this is true because after multiplying the digits by the corresponding powers and adding them up, we get 265. So in this base, we will also use digits from 0 to 6. To sum up, in base a over b, digits represent different powers of a divided by b. If a is bigger than b, we use digits from 0 to a minus 1, but if b is bigger than a, we use digits from 0 to b minus 1. And if we want to convert a number to base where b is bigger than a, we first convert this number to base b over a and reverse it. The real numbers, apart from containing rational numbers, also contain irrational numbers. Those are numbers that can't be expressed as a ratio of two integers, and written in base 10 have an infinite decimal representation. For example, the square root of 2, the cube root of 5, or pi. First, let's look at number bases of square roots. For example, base square root of 5. In this base, digits represent powers of the square root of 5. This base has a lot in common with base 5, because the square root of 5 raised to the power of 2 is equal to 5. The square root of 5 raised to the power of 4 is equal to 5 to the power of 2. In general, the square root of 5 raised to the power of 2n is equal to 5 raised to the power of n. So to express any number in base square root of 5, we only need to use the same digits as in base 5, that is, from 0 to 4. For example, 97 in base square root of 5 is written as 30402. This number, represented in base 5, is just 342. The digits that represent odd powers of the square root of 5 are all equal to 0. This will be true for any rational value. But in this base, we can also easily express irrational values that are multiples of square root of 5. For example, 123 in this base is equal to 8 plus 2 times square root of 5. Here, the digits representing the odd powers are not equal to 0. With the same logic, we can create number bases of higher roots. For example, the fifth root of 7. Fifth root of 7 to the power of 5 is equal to 7. And generally, the fifth root of 7 to the power of 5n is equal to 7 to the power of n. So in this base we can use the same digits as in base 7. 36 in base 7 is represented as 51. To express this value in base 5th root of 7, we just have to write zeros where the powers of the 5th root of 7 are irrational. Like this, we can create a number base from any root of any number. All roots are algebraic numbers, which means that they can be a solution to a polynomial with rational coefficients. But irrational numbers also include transcendental numbers, like pi or e. Let's see how base pi works. In base pi, digits represent different powers of pi, but it isn't clear what digits should we use. Maybe the same digits as in base 3, because it is the closest integer to pi. But then, the only integers we would be able to express in this base would be 0, 1 and 2, because only pi to the power of 0 gives us an integer. Just as pi in base 10 has an infinite decimal representation, 10 in base pi would also be infinite, as would all other integers. So theoretically it is possible to create base pi, but it doesn't work as good as algebraic number bases. The same is true for the number e, which is also transcendental. But surprisingly, base e is special in a way. To explain why, we first need to talk about radix economy. Radix economy is a way to measure efficiency of a number base. For example, in base 16 we can write all values between 0 and 255 using only 2 digits. But in base 16 there are 16 possible symbols each digit could have. On the other hand, in base 2 we have only 2 possible symbols each digit could have, but to express all values from 0 to 255 we would need 8 digits. The radix economy is calculated for a number written in some base. For example, to calculate the radix economy for a number 231 written in base 10, we take the number of digits used to write that number, in this case it is 3, and multiply it by the total number of symbols in that base, in this case 10. So the radix economy of the number 231 written in base 10 is equal to 30. Radix economy for a number n written in base b can be generalized by this formula. We can graph this formula for b equal to 10. To better see this function, the horizontal axis is in the logarithmic scale. We can see that the function jumps when we add a new digit. But when n gets very large, the jumps become less and less significant. Which means that for large values of n, this formula can be approximated by b times log of b of n, and that is equal to b times ln of n divided by ln of b. So, if we want to know which number base has the smallest radix economy, we just need to know for what b this part is the smallest. We can graph this function and we can see that it has a minimum at the number e. So it means that base e is the most efficient number base. But as we have seen with base pi, transcendental numbers don't work so well as bases. So this information isn't very useful and it's here just as a fun fact. So we now know that all real numbers except 0 can be a number base, although some of them do not work as good as others. Outside the real numbers, we have imaginary numbers. Imaginary numbers are real numbers multiplied by the imaginary unit I, which is equal to the square root of -1. We can create number bases using imaginary numbers, and they can even express both real and imaginary numbers. For example, base 3i. In this base, digits represent different powers of 3i. 3i to the power of 0 is equal to 1. 3i to the power of 1 is equal to 3i. 3i to the power of 2 is equal to -9. 3i to the power of 3 is equal to -27i, and so on. This creates a pattern where you have a positive real number, then positive imaginary number, then negative real number, then negative imaginary number, and then again positive real number. But what digits should we use in this base? In base square root of 5, we use the same digits as in base 5. 3i is equal to the square root of -9. So in this base, we will use the same digits as in base -9, that is, from 0 to 8. This allows us to express any real and any imaginary number, but this base also allows us to represent numbers that have both the real and the imaginary part. For example, 7,2 in this base is equal to 21 plus 2i. As we have seen, we can create number bases from almost all real numbers and pure imaginary numbers, but unfortunately we can't create number bases from all complex numbers. For example, let's look at base 2 plus 2i. In this base, the digits represent different powers of 2 plus 2i. 2 plus 2i to the power of 0 is equal to 1. Then we have just 2 plus 2i, then 8i, and so on. Any number to the power of 0 is equal to 1. That allows us to express all integers in any base if we use the right digits. But in complex number bases, we also want to express all complex numbers. Here, the smallest multiple of I is 2. So we are only able to express multiples of 2i. We can't express any odd multiple of I in this base. When we wanted to express any multiple of I in a pure imaginary number base, we could just use negative powers. For example, in base 3i, we had powers 1, 3i, -9, and so on. And all other powers were a multiple of 3i, but 3i to the power of -1 is equal to 1 over 3i. And when we multiply the numerator and the denominator by 3i, we get that this is equal to -i over 3. So if we wanted to write 4i in this base, which is not a multiple of 3i, we could just take 2 times 3i and 6 times -i over 3. So 4i expressed in base 3i would be 20.6. So to be able to express all imaginary numbers in complex bases, they need to be of form n plus or minus I. But that is not the only problem. Let's look at base 1 plus I. In this base, we can express odd multiples of I. For example, 110 would be equal to 1 plus 3i. But let's look closer at the powers we can use. First we have a positive real number, then positive real and positive imaginary, then positive imaginary, then negative real and positive imaginary, then negative real and negative imaginary, then negative real, then positive real and negative imaginary, then we again have a positive real and the cycle repeats. We can see a pattern here. We have 3 positive imaginary values and 3 negative imaginary values. Then we would again have 3 positive imaginary values. Real values create the same pattern. To express all values in this number base, we would need too many digits, because we have so many positive values next to each other and so many negative values next to each other. But now let's look at base -1 plus I. In this base, the pattern in powers is very different. Real and imaginary values alternate between positive and negative. This allows us to express any number using only digits 0 and 1. But we only changed the positive one to negative one in the base. Let's see what happens when we change the I to negative. We can see that in base 1 minus I, we still have a pattern where the positive and negative values are in groups of 3, but in the second base we have a pattern where the positive and negative values alternate. So the pattern doesn't depend on the sign of I, but it depends on the sign of real number. We can change 1 to any other natural number. For example, base 2 minus I and -2 minus I. In the first base, the positive and negative values are again next to each other. In the second base, positive and negative values are not exactly alternating, but they are not in big groups and that will still allow us to express any number. So now we know that the complex number bases have to be of form -n plus or minus I. And to express any complex value in those bases, we only need to use digits from 0 to n. To see how this works, let's go back to base -1 plus I. In this base, we can express any number with digits 0 and 1. For example, to express 11, we start with 16, subtract 8 and 8i, add 8i, add 2 and 2i, subtract 2i, and add 1. That's a complicated way to express 11, but one thing the complex bases are good at is expressing imaginary and complex numbers without the use of the letter I. For example, 7i expressed in this base would look like this. All those unusual number bases are interesting to explore. Some of them have advantages and some of them are just useless. So maybe, to not overcomplicate things, we should stick to base 10 for now.